You can hear me? Okay, my name is Łukasz Wyrzykowski. If you find it difficult to pronounce, I normally put it here on my slide, so then it makes it a bit easier. Okay, so we've seen this picture. It's kind of more in advance. You've seen the black holes and neutron stars from gravitational waves, but there are two questions emerging from this image kind of immediately. Are some of these dark matter? This question kind of was revived recently. People suspect that some of these very massive ones are actually the primordial black holes produced at the very early universe. So that might be partial solution to the dark matter problem. And then there is this gap here, which should not be there, at least to some theorists. Some theorists say it should be there, some people say it shouldn't. So there are these two questions which we can address with microlensing. I will just quickly go through the history of dark matter searches, especially for the younger audience. As Paczynski suggested in 1986, if we can probe the halo of the Milky Way by looking at the Magellanic Clouds as sources and look for lenses due to compact objects called machos. And if we see an excess of microlensing events on these sources here, we can then estimate the mass spectrum and actually claim the dark matter is at least partially composed of compact objects. So these are the results. This is a kind of a summary of some most important papers. We analyzed OGLE 2 and OGLE 3 data spanning 12 years of monitoring of Magellanic Clouds, and we found very few microlensing events there, so we could explain all of them by self-lensing, so stars in the LMC lens stars of the LMC. So we could put these constraints. This is the OGLE-based constraint on the macho halo mass fraction. So we can combine with EROS here, which was more sensitive for lower masses. We push this envelope here to something like a very few percent. It's in a conservative approach. I will also emphasize that OGLE provides the tightest constraints on machos below 10 solar masses. So the conclusion here that there is no machos in this mass regime, and interestingly, this mass regime here above 10 solar masses is where the gravitational wave black holes sit. So we don't have, let's say so far we had low sensitivity in that mass regime. So this window is still kind of open for possible dark matter companions. Black holes, for microlensing, there were some searches before already. This is one of the best examples from Dave, and this is one from Shude. I will emphasize that this one is still the longest timescale microlensing event found so far in 1999, so with timescale of 640 days. There were some candidates for remnants, black holes or neutron stars in binary lenses. I will mention these two papers. So the masses there were estimated and measured, and potentially these contain black holes or neutron stars as well. So I'm showing some preliminary results also from our work on population synthesis with Grzegorz Wiktorowicz. So we simulated the binary systems. As we know, all stars are in binaries at some point. And then we produced black holes in actually we found that there are two channels in which black holes are mostly produced. The one is by disruption of a binary system, and the second one is by merging of these binary systems. So these are more abundant, and these are actually faster. So we could estimate the distribution of timescales of black holes from these two channels, and we can see that disrupted binaries, they tend to have slightly shorter timescales, even at around even below 100 days. And the mergers, they can produce slightly longer events. But the conclusion from our simulations is that also these black holes resulting from binary systems, they are actually even more abundant than single black holes produced by single stars. So there should be about 50 events due to single black holes. I mean, they're single now after being disrupted or merged. There should be 50 events in OGLE for every year. So as already said by Chris and Kasia, that we need Gaia astrometry and well, astrometry and photometry combined to disentangle which events are due to what. So, but we did some search in Ogle 3 already. Ogle 3 spanned 2001, 2009, and it observed 150 millions of stars in the bulge. So first we found 3,500 standard events there. Until recently, that was the largest sample. Now Przemek Mróz has superseded this with Ogle 4, of course. But in the same sample, we found 59 high-quality parallax events. By high quality, I mean the parallax, the annual parallax is clearly visible there. Of course, there is a range of events, I guess, with much smaller parallax, but we looked for events with strong parallax, so then we can constrain the mass of the lens of potential black holes using this signal. So we found 18 events with probability larger than 75% that they have remnant and dark lens, and among these, we identified 8 black hole or neutron star lens candidates with even higher probability. So here are some examples of these events. So you see, these are fairly long events, and they exhibit very nice annual parallax. This one is actually very spectacular. And this one is our most heavy candidate. So in order to derive the mass, this mass we claim here, we had to do some hand-wavy, well, Bayesian, typical Bayesian estimations, because we are still missing the theta e. So we were using some proper motions of the sources and proper motions of the lenses, just assuming the typical distributions of distances and proper motions in order to derive these probability density maps for mass and distance. So you see they're fairly well concentrated for these cases. This one is stretched, but it's still very well constrained because of this nice parallax. We can improve on that. We can by using Gaia Data Release 2. So this is the map of sources. This is not an image. It looks like an image, but it's a map of sources in Gaia DR2, which was released in April 2018. The catalog contained parallax and proper motions of 1.3 billion stars, and it was based on observations by Gaia taken between 2014 and 2016. It means that for the sources which were lensed in Ogle 3, which was like 15 years ago, then there is no impact of astrometric microlensing on these sources because they're many years after the event. So we could use Gaia in order to use distances to the sources and then constrain the proper motions. Instead of hand-wavy way and Bayesian way, we could actually have actual measurements. I'll take a moment here to tell you that distance is not 1 over parallax. So they taught you wrong at your universities. Because, and especially in Gaia Data Release. So parallax, which is measured by Gaia, is a noisy measurement of 1 over distance. I hope you remember that well. So we can use the parallax measurement from Gaia. They can be used to infer the probability distribution on distance, right? So that's the proper approach to Gaia DR2. So I hope you will remember that. Moreover, 25% of sources have negative parallaxes in Gaia. This is nothing wrong. As I said, parallax is a noisy measurement of 1 over distance, right? So it can happen that these will end up on the negative scale. You can use, in order to properly use Gaia DR2, you need to remember about all these. And you can derive the probability distribution for distance of the source for every single one. Actually, you don't have to do that. You don't have to do that because Corin Byler-Jones, he did that already for us. So he published a catalog of distances to 1.3 billion stars in Gaia DR2. So actually now, if you're lazy, you can just take his catalog.
Hopefully you're not lazy because it's totally inappropriate for bulge sources.
Yes, that's right. For bulge sources, there are some caveats there, but still, this is the best what we have, right? And this catalog is nicely available via ESA or Sinbad or even TopCat, which I strongly recommend you to use. So anyway, so we could use Gaia proper motions, in particular proper motions, but also distances to source stars. And then, so we infer that there's 18 dark lenses from Ogle 3 parallax events. So this is the This is the kind of noisy. So each curve here shows you one microlensing event for which we derived the mass distance relation probability distribution. If you marginalize over distance, this is the probability density we get for a mass of this lens. So if you plot them all and then we plot the medians here, you see that the most striking feature here is that there is a continuum of masses from 1 to 10 solar masses. This is something different what people see in X-ray binary systems, where there are neutron stars here, there's a clear cutoff, there's a gap, and there are black holes all above 5 solar masses. So there's a hint that we can actually exclude the mass gap. We can at least partially exclude the mass gap using this small sample of dark lenses. Yeah, this is what some theorists say, that there should be a continuum from neutron stars to black holes. I will tell you briefly about one additional source we found among our parallax events. So this is a map of Ogle 4 sources for which there are Gaia parallaxes. So some of them have negative parallaxes, the black ones. Most of them, as you see, Ogle is a little bit deeper than Gaia in the bulge. Some sources are not being detected by Gaia. But anyway, this guy here, it happened to have a parallax of 6 milliarc seconds and high proper motion. Moreover, we found that this was a microlensing event. So one of our parallax events. So what we found, there is blending, which is very, very severe. It means that Gaia sees actual lens, right? So the source there is about 20 magnitude, and the lens is about 18. So we can use these measurements as they are for the lens. So it means that for this event, combining the Gaia information and the microlensing parallax, we can derive this lens mass and lens distance probability distribution, and we can actually solve this event. This is a 0.4 solar masses at 180 parsecs lens. Interestingly, this source, the absolute magnitude is about +12, which is a little bit too faint for its mass. So I don't know why, but that's what we see. It should be few magnitudes brighter. I don't expect much of the extinction to this distance. Maybe that's not a main sequence star. It could be a sub-dwarf or something like this. So in summary, I'll say that dark matter halo compact objects below 10 solar masses are excluded with Ogle. Galactic black holes can have significant natal and disruption kicks, what we found in the synthesis. So we can expect some of the black holes to cause shorter events than previously thought. And we are missing 50 black holes every year, actually. So Ogle 3 parallax events plus Gaia DR2, we can use that to infer the masses of some of the former old parallax events. Remember this distance is not 1 over parallax. And we see there's a hint for no mass gap between neutron stars and black holes. And astrometric microlensing is essential. So we're continuing the hunt for black hole lenses as seen in Gaia. And there should be hundreds of black holes in LSST and WFIRST, but I will emphasize that astrometry is essential. My last note is that I'm looking for a postdoc to help us with this black holes with Gaia and microlensing. So I will finish with the same plot I started with. This is the masses of black holes and neutron stars from gravitational waves. And if we add the best examples of black holes we found from microlensing, we see we're starting filling the gap between these. Thank you.
We have questions for 1 or 2 quick questions. Dave?
So there's one thing that your analysis, in particular your Bayesian analysis, doesn't seem to consider, which is the kicks that black holes may get when they form. Mm-hmm. And this can be something can be measured about the kicks for black holes and X-ray binaries. And the models trying to explain black hole X-ray binaries tend to predict very high scale heights near the local disk, and the scale heights get a lot smaller toward the inner disk and the bulge, where there's much more mass to keep the
Yep.
black holes in the disk. So it seems to me that the best way to look for black holes is actually to look for long events with a very small parallax, and ones that you're inferring that are a few kiloparsecs away. I think there's a good chance that the black holes that were originally there have been moved to much higher scale heights.
Right, but I'll emphasize that we assume the stellar motions for the black holes, and that gives us the lower limit on the mass. If there was a significant kick, then the masses we would infer would be much larger. That's
Well, I mean, my point was that the probability of having those black holes in the disk would be much smaller if they get big kicks.
right. Yeah, well, the ones we found so far are in the bulge, right? So that's what you said.
Well, I mean, the events are in the bulge, but you're inferring that the black holes are a few
They are
kiloparsecs
nearby,
away.
yes.
And so if they're getting big kicks, then there wouldn't be very many black holes a few kiloparsecs away.
Mm-hmm. Sure, but well, we think that these are single ones, right? So they might have not experienced the kicks, the single ones here, right? So that they may remain in.
There's mechanisms for kicks for single black holes.
True.
The supernova don't have to be.
They are not asymmetric.
They're not symmetric,
Yeah.
and when you make a black hole, you convert a lot of mass into energy.
Sure.
So.
Well, the kicks are one of the main questions as well, the mass gap as well, and so we can actually infer the something on the kicks from microlensing as well. So these are just the detections, and you're right. Well, we don't include that in the Bayesian analysis.
Maybe one quick question.
I was wondering if you had considered the Gaia source that you showed at the end, whether it was a white dwarf or is it too bright to be a white dwarf?
It's too red.
Too red. Okay.
Yes. Yeah, I wish it was a white dwarf, but it's not. Okay. Thank you.
Our next speaker is Abdulrahman. I hope that's not too wrong. She'll talk about the late-time high-resolution images of black hole candidates, microlensing events from machos.
Okay. Wait, can you hear me now? Oh, awesome. Cool. So yeah, I'm Fatima Abdurrahman. I'm a third-year grad student at UC Berkeley working with Jessica Liu. And I'm going to be showing some work me and an undergrad also from Berkeley, Haynes Stevens, have been working on for the past year. Gonna take this off because it's still not being quiet. And I'm going to present, after the perfect setup by Łukasz in the last talk, two specific black hole candidates from the Macho survey, Macho 98, bulge 6, and 96, bulge 5. So these are the two black hole candidates that I'll be talking about. You might have seen the same one or remember it, or sorry, this one from literally one talk ago. Both of these events were detected back in the 90s, so it's been a good 20 years since either of them have peaked. They were detected by the Macho surveys, looking for compact objects by microlensing. And previous analyses of these objects' light curves from the Macho data have put mass estimates at about 6 solar masses. Though there's pretty generous ranges on those masses because, as Łukasz just said, these are generally statistical arguments where you have to be a little bit generous with what constraints you can put on any of the parameters, since there isn't some secondary source of information such as astrometry to break degeneracies. Additionally, work a little bit later has put MB96 at about a 37% likelihood of being a black hole and MB98 at 2.2. And I'm going to argue that either of them have a good case of being a black hole, which I think is a little bit higher than this number. So what we're going to look at 20 years later is some new data, particularly high-resolution near-infrared images from Keck's NERC-2 taken in 2016 and 2017. Information from Gaia, for which there is a source for Macho 98. And we have the advantage of 20 years of proper motion separation. So the idea is, if there is a sizable relative proper motion between the source and the lens is luminous, we should be able to look in these images and find the source, find the lens. And if we can't find a lens, that suggests that it's a compact object. So I'll use all of this data to answer a single question. Can we see a lens? It's my only goal here. All right, so what I'm going to do is explain the analysis in detail using one of the targets. This is MB98 as the example, and the other one was analyzed in a similar fashion. So this is a NERC-2 image. That is Macho 98 bulge 6. It's taken at Keck's KP band. We have data from on both targets. We have data from the summer of 2016 and 2017. And the process for looking for a lens here is first identifying nearby and bright PSF stars that we use to reconstruct the image PSF, which we then use to find all of the stars in the image. Now, we don't care about most of this area. We only care about the central 1 arcsecond. So we're going to zoom in there and see what we find. So in 2016, with this being the target, these were additional sources found with a pretty smooth residual. This is an HST image in 2000 of the same target, and as you can see, you have the same stars existing around it, but there's nothing additional to see in this image. So I think with that, I can say it's a black hole. My talk is done. This is super easy to do, right? Thanks. But in reality, it's a lot more complicated than that because we have to determine what our detection limits are. So that's the crux of this analysis. So to determine a detection limit, the method used here is planting stars in the image and then determining what can be retrieved. So fake stars were created with that same PSF determined by those bright stars in the first images. And the magnitudes were scaled to range from about 23 to 12. And then those, one at a time, a star created from that PSF at some magnitude is placed centered on some pixel, going through all of the pixels within 0.5 arcseconds of the source. And then the exact same star finding routine was run in order to see if that new source was able to be detected. So there were many iterations done within a very small area. And then looking back at the results of that, if a particular planted star at some radial offset from the source star and some magnitude was detected 95% of the time, then we call it detectable, and that's what this line here is. So we should be able to confidently detect anything above this line. So given this completeness curve in radial offset and magnitude space, we can combine that with synthetic isochrones. We used 100 million years in order to try to get the entire main sequence without pre-main sequence objects. And we can convert this information basically by saying, for a given magnitude, for an isochrone at a given distance, what is the minimum mass source that we find? So in that way, magnitude becomes distance and minimum mass pairs. Similarly, the radial offset maps to proper motion. If you think about the two source and lens being overlaid at the time of peak, and then some proper motion in 20 years has given us some radial offset. So we can combine all this data and map it in that way in order to determine a detection limit. Very interesting plot, right? So it's complicated, so I'll build it up slowly. So first, we're not going to look at anything with a relative proper motion less than 2.5 milliarcseconds a year. This represents about 50 milliarcseconds from the center of the source, and we don't have the resolution to detect that. So above that, let's throw a star on here. So for a given star from our isochrones, and using that completeness curve, at a given distance to the lens and relative proper motion, we have some minimum mass, right? If we increase the relative proper motion, then you can imagine that the star would have moved farther away and therefore will be easier to detect because it's not hidden in the source PSF. And so our minimum mass that we can detect goes down. We can detect more. Conversely, if you increase the distance to the lens is farther away, gets dimmer, so we have poorer detection and our minimum mass goes up. So we can complete this whole space with this same technique. And you'll notice that there are some gaps over here. These gaps are combinations of these parameters for which there were no stars in the isochrones we created. So we could call this dark objects, black holes and neutron stars. Okay, so this is our detection limit in mass, lens distance, and relative proper motion space. However, I haven't really said anything at all about the microlensing event. This is really only what we can detect with these images that I've been looking at. The microlensing comes in with this curve. This is taken from a fit in Poindexter 2005, where, as we know, there's a degeneracy between the lens distance and relative proper motion. And so the lens that caused the event would have to fall within this green band. So the combination of the green band and our detection limits show what is allowed for this event. And this entire thing was done for Macho 96 as well. The curve here was taken from Bennett 2002 instead. So we have two different sets of data on two different targets with the allowed sources that we can't detect marked here. Anything above these masses we should have been able to find in those images that we were looking at, but we didn't find anything above that. You might notice that the distance to lens is a lot more constrained in the case of Macho 98. And the reason for this is that, by lucky coincidence, it is a Gaia source, and remarkably close in at that. We have a distance in Gaia of a little less than 2 kiloparsecs. Here you can see where it falls in the nearest, within a box of about 36 arcseconds by each side, all the Gaia sources in that region with their proper motions, and as a point vector diagram over here. So we have a very close-in source. The thing is, this is most useful if we know that there is no lens flux, because if we have two stars overlaid very closely and we can't resolve them and they're moving in two different directions, whatever proper motion or parallax you get out of that is going to be a little bit, it's not going to be ideal. So to kind of combat that, we can look at how much blending we expect to see versus the stars in the image. So previous constraints on the blending parameter for this particular event, based on light curve fitting, have been around 65 to 70% of the light coming from the source is from the star, where the other approximately 30% is coming from something else, whether it's a luminous lens or background stars isn't exactly defined. So what I did was going back to archival HST data from 2000 and looking within the central 1 arcseconds of MB98 and seeing if there is anything else in that region that's detectable with higher resolution images than the photometry was originally taken that could account for that flux. And lo and behold, if you just add up the fluxes of the star and calculate it by hand, you get about 75% source flux, which is in agreement with the previous estimates from light curve fitting. So we can say here that the blending is likely attributed to stars around and not a lens. So that makes me a little bit more confident in this Gaia measurement accurately representing the source. And unfortunately, the other target, Macho 96, was not in Gaia. However, it is still useful because Gaia sources can be used as an absolute reference frame for which we can do with which we can do astrometry. And where is it? There we go. So this is Macho 96 calculated by the 2 epochs of Keck data that we have using all of the Gaia sources as the reference stars. And these again are all of the reference star or all of the Gaia sources within a 36 arc second box around the source. So you can see it falls into the same range of values and doesn't look like I'm completely miscalculating this. So the proper motion for the source here with very generous error bars is around 6 milliarcseconds here. So for my conclusions, rather than try to summarize a pretty large amount of data in a pretty concise way, I'm just going to say that in either case, no new stars have been found within the central 0.3 arc seconds of the source. These are constraints on detections, our detection limits, and these are what we know to be, or think to be the source proper motion, specifically the source. Note that this proper motion is the relative proper motion, which we cannot constrain well. However, with proper motions this high, it's a fair assumption that a lens and source aren't going in the exact same direction with that speed. And we additionally have the distance to source in this case. So with that, I will leave this here and take your questions.
Questions for Fatima? Yeah, Matthew?
So looking at these plots, it seems like you've got some fairly massive lenses. So I've got 2 questions. So can you use just photometry to rule out some of this parameter space?
Sorry.
And the second question is, are you considering white dwarfs?
So first question, when you say photometry, do you mean from fitting the light curve or just from?
No, like the total amount of flux in your images.
So one thing that I'm kind of working on concurrently with this in trying to constrain this portion of the plots is exactly that, looking at broadband photometry from different sources and trying to construct a rough spectrum on that based on that to see if we can see a second source in this spectrum. My preliminary work, which I wasn't completely confident to show, suggests there's not. In both cases, they look already like one source without anything strange in the SED. And in regards to white dwarfs, haven't explicitly talked about them or looked at them here, but I guess the thing to look at this in conjunction with is the other mass estimates on the lens, which are far above either white dwarf or neutron star masses. So this on its own isn't necessarily completely informative in telling the whole story. It's kind of a follow-up to other people's determinations of masses. These are just our lower limits.
So I had a couple questions. First of all, I'd recommend that you do the similar thing for Macho 99 Bulge 22, which is probably a better black hole candidate than either of these.
Okay.
And then I was a little wondering why you used my models instead of the Poindexter models for Macho 96 Bulge 5.
So I think it originally both of them were actually yours. I had updated this one, but I don't think 96 Bulge 5 was. And wait, did you ask why I didn't use yours, or why did I use yours as opposed to Poindexter?
Yeah, why? I mean, I think I missed one of the degenerate solutions, and the 2 solutions in Poindexter are similar, but they have slightly different source star flux.
So the undergrad that I was working with, Haynes, had initially done them with yours. I've been working on this target more, so I have updated it with different data, but I just hadn't bothered changing the first one.
I would recommend you use the Poindexter one instead of mine.
Okay. Thank you for that.
Okay, let's thank our speaker again. speaker is Alice Zorlo, talking about measuring the mass of Proxima Centauri from a microlensing event.
Is it working? Yeah, perfect. No, I have to use this one. Okay, thanks. All right. Hello, everyone, and thanks for the invitation. My name is Alice Zurlo, and I'm a faculty at Universidad Diego Portales in Chile. And today I will talk about the measuring of the mass of Proxima Centauri using a microlensing event. This is a work that I've been done in collaboration of all this year consortium. So Proxima Centauri, as you may know, is the closest star to our solar system. It is part of the triple system with Alpha Centauri A and B. And also, a couple of years ago, in the Pale Red Dot campaign, they found an Earth-like planet with a period of 11 days around this star. So this is a very important star for us, and but we have so far just a measurement of the mass with the mass luminosity relationships. So Kailash was actually, and collaborators were actually talking just after myself, proposed in 2014 to follow up Proxima. This is an HST image of October 2012. And you can see this is in green, this is the expected motion along the sky of Proxima. Proxima is a very fast mover. It has very high proper motions. And you can see that it is approaching two background stars, source 1 and source 2, in two different epochs, October 2014 and February 2016. You can see that the closest approach is during the second close encounter to source 2. And we can take advantage of the approach into this background source because a microlensing event is been happening, and we can measure the mass of the lens, in this case, Proxima Centauri. So this is the expected effect that we can have. The source, in this case, the lens, in this case, Proxima is in the center in green, and you can see in black what we expect to be the shift of source 2 in this case. This effect is very tiny, is about 1 milliarc seconds, so we need very accurate astrometry to measure this effect. And I want to mention that the same analysis has been very successful to measure the mass of white dwarf, this time 2051b. And this is a very nice result published by Kailash and collaborator on Science, because this is the first time that we can measure the deflection of the light, the astrometric deflection of the light of another star other than our sun. So we try to do the same analysis from the ground, as you see. So the other results have been possible with the HST telescope from space, and we try to do the same thing with SPHERE from the ground. SPHERE is an high contrast imager, and it's a planet finder dedicated to the characterization and the detection of extrasolar planets via the direct imaging technique. So you can see here an example of how this is working. We have in the first image the PSF of one star without the extreme adaptive optics working. Then we can see that with our extreme adaptive optics on, we can reach stereo ratio of the 90% in the H band, and we can reach contrast very close to the star of about 10 to the minus 3. Then we use apodized Leo coronagraph This is just the same math that we were using to study our sun. And with that, we can reach contrast of 10 to minus 4. But when we applied all the post-processing techniques of the direct imaging, we can reach very high contrast of 10 to the minus 6 at a very close separation, here in 300 mass. So this is a cartoon of the instrument sphere. It is mounted at the Very Large Telescope in Chile. And it is composed of a common path, which is giving light to the three subsystems. One in simple is the only one that is working in visible light, and it's a polarimeter. And then we have IRTIS and IFS. IRTIS has the largest field of view of the instrument. It's 12 arcseconds square, and it is a dual band imager camera. And then we have the IFS, which has a smallest field of view of 1.7 arcseconds, and it is divided in thousands of tiny spectra. It is used to study the very interior part of the planetary systems. During all the observation of Proxima, these two instruments, IRTIS and IFS, worked in parallel together. And I just want to convince you that we are capable of very, very accurate astrometry. This is our favorite direct imaging planetary system around the star HR 8799. This is the orbital monitoring. And you can see here there are all the collection of astrometric points with the other instruments. And then, where's the pointer here? And then you can see the pink dots here are our measurements. You can barely distinguish the error bars because our astrometry is very, very accurate, of the order of 1 milliarcseconds for these planets. Then coming back to Proxima, we follow up the star for 2 years, starting from March 2015, and we obtain 9 epochs. And you can see the final images for the two detectors. This is IRTIS. You can see source 1 and source 2. And here source 2 in the IFS field of view. You can see that with the capability of sphere, of the having a very high contrast and very close to the star, we can clearly see source 2 in the detector. And then also we used all the images and all the data that we collected to put upper limits on a possible giant companion of Proxima b. We are not able to rule out very low mass planets as with Gaia, we saw already in the talk by Alessandro. And we can say that we exclude masses above 4 Jupiter masses for this system. So here is all the stars that we identified during the 9 epochs, and you can see this is Proxima, the blue stars here, and the movement on the sky. We just completed like a sort of catalog of all the background stars that we could see in the detector of IRTIS. And I just want to stress that the only bright star available and that we could use to measure the microlensing effect is source 2, because all the others are too faint. So here the size of the points is rescaled with the flux.
So source 1 couldn't be used?
It was too late because we started in 2015 the campaign, so it was already here. It's too far away. So now we just use the second source. So as we need very high astrometry for this purpose, we use an MCMC analysis to adjust all the detector parameters. Remember then that Proxima is always behind the chronograph, so we need to recalculate the centering, the pixel scale, and the true north for our epochs, and to recalculate proxima movement. And we use all the background stars as a grid. And you can see what we had as a result of proximal movement in comparison to the Gaia data release, the second data release. And you can see they are very, very similar, but remember that we calculate all these, the parallax and the proper motion with respect of the background stars. So this is not an absolute measurement, it's relative to the background stars. And then this is our result. This is the model of the separation in millisecond due to the microlensing event. So this is the separation of source 2 with respect to Proxima. And we model this microlensing event, and we recalculated the mass of Proxima, this time the gravitational mass of Proxima, which is in agreement with the mass luminosity relationship that gave 0.15 solar masses. So, and also we had a big surprise during the last Sphere GTO run that I didn't expect it. We found another star in the IFS field of view that I thought it was too faint to be detected, but it's there. So stay tuned, because we will probably be able to reduce our error bars on the mass of Proxima, collecting all the data that we had together with this new microlensing event. I still have some time for the summary. Proxima Centauri, even if it's the closest star to our solar system and also has a planet around it, has still large incertitudes on its mass measurement. We used a microlensing event in February 2016 to recalculate the gravitational mass of Proxima, which is 0.145 solar masses. And this is the second time that we can measure the gravitational deflection of the light by a star other than our sun. Thank you. I will be happy to take any question.
Questions?
Okay. What about the possibility of a planet around Proxima Centauri that contributes to the microlensing signal? Well, the signal you get has large error bars, but indeed, if there is a planet around the Proxima Centauri at the right position, it could give a contribution to the microlensing signal. Have you checked this possibility?
Yes. So no, I haven't personally. Kailash did it in the paper of 2014. There's all the simulation of the expected signal by a planet around the star. But in our case, we couldn't have the spanning and the frequency of observation, because as you saw, we have 9 epochs in total, and they are very separated in between each other. So you need to a very high cadence to monitor such a signal.
Just following up on
that, the known planet or candidate planet around Proxima Cen is fairly short period.
11
so I think
days.
that would be well inside the Einstein ring, and so probably wouldn't create much of a perturbation at all. Although you could search for planets that are more distant than the candidate planet.
Exactly. Yes, but in any case, we have a strong constraint on the mass of a possible other outer planet. So as Alessandro studied one Jupiter mass with Gaia.
For the constraints?
Yeah.
Less than 1.
Less than 1.
Down
So
to a 10 Jupiter mass.
okay.
Andy?
Well, went by a little fast, but I thought that your chi-square per degree of freedom looked higher than 1. How did you determine your errors on that in the astrometric measurements?
Yeah, that was very complicated because we had.
Can you show that slide again?
This one?
Yes, maybe not. It looks a little high. Yeah.
So yeah, the error bars, especially for the biggest error bars, the first point is because the star was at the very edge of the detector. So we had huge error bars. So we took into account all the errors in the astrometric signal, and we tried to be very conservative too. So maybe they're bigger than they should be.
All right, let's move on. Let's thank our speaker again.
Thank you.
So next we have Kailash Sahu talking about let's see, astrometric microlensing with HST.
Thank you. Okay, thank you. I'm on, right? Okay, yeah. So I will talk about some astrometric microlensing projects that we have been doing with HST. So this is a lot of people are involved here. Those are the people who have been involved. I will speak. I plan to talk about 3 different projects. So the first one, which Alice already mentioned, the mass determination of a white dwarf, of Stein 2051b. Then I will talk about the search for intermediate mass black holes in globular clusters. I will probably not have enough time. I kept it last because this is being talked by others as well. So, but I will just talk about only the summary of the search for isolated stellar mass black holes. So this is a simulation which tells how the white dwarf as it goes by, what you would expect. This was made by our OPPO people. So this long before, of course, Gaia now has wonderful proper motions. We can now predict the encounters to within 10 milliarc seconds. But well before that, we took all the high proper motion stars to see whether there are any of them will actually lens, because you did not really need very high accuracy. Even if it is 0.1, 0.2, 0.3 arc second, accuracy is still enough for these kind of events. So, and one very interesting among all, there are several such close encounters. One very interesting one I thought was by Stein 2051b, mainly because white dwarfs, the mass radius relationship is a very fundamental parameter for a white dwarf. And there are not too many such observations of mass radius relationships. In particular, there are about 3 direct mass determinations for white dwarfs, and all those 3 were actually in binaries. And binaries may not be quite representative of all white dwarfs, particularly since there is maybe mass transfer, and these were relatively close by. So it was important to have a mass determination of a rather isolated. This Stein 2051b actually is also in a binary, but the companion is more than 55 AU away. So this is effectively isolated. So we observed this one. So this is the this is fast observation of HST, then we could predict what will happen. So the source happens to be here. The source is about 400 times fainter, that is the challenge. So we have to, when it comes here, we should still be able to measure the mass deflection to less than milliarc second. So this is the actual, let's see, should move. Okay, so this is the actual motion. So everybody knows what happens to parallax, but many of you probably have never actually seen the parallax motion. So this you see these are the actual HST observations at different times. So here is the time 2000, as it moved from here, we observed at these epochs, and the closest 2 epochs were the ones actually which gave the highest deflection. So this was already shown before. So this is the X and Y deflections. So as you see, this is the model in X and in Y direction. I'm not showing all the figures, but so this just shows you what the accuracy that we achieve. And this suggests that the theta E Einstein ring is about 31.3 plus minus 0.5 milliarc seconds, which corresponds to a mass of 0.675 plus minus 0.051 solar mass. And this particular white dwarf was interesting in the sense even with this 55 AU separation binary, people had actually tried to measure the mass of this, and this did not fit within the mass-radius relationship. But that was fairly uncertain measurement. Here now, after we measured this mass, when you put this in the mass-radius relation, it falls exactly on the predicted point. In fact, before that, it was somewhere here, which would suggest it's an iron core white dwarf, and nobody knows how to make an iron core white dwarf. Anyway, so this was actually, I was pleased that in the year, the Discover magazine comes up with their best, the 100 best science results, and this was listed as one of the in the whole of science. I like the first sentence. This is, the astronomers put a white dwarf on a scale and watched the needle move. That was pretty cool. Okay. So then the rest, next one, Proxima Centauri, actually, Alice already told, but we have also observed with HST at these epochs, and we observed till 2018. We have just finished the analysis, so these results are coming soon now. Now I want to move to the search for black hole microlensing signatures in globular clusters toward the galactic bulge. So the supermassive black holes, they're found in almost all galaxies. They are more than 1 million solar mass. They're fairly common. And of course, stellar mass black holes have also been found, but no intermediate mass black hole. The mass gap between not between 50 and 10, but there is the intermediate mass of 100 to 100,000 solar mass black holes have never been found. And centers of globular clusters are the most promising sites where you would find these intermediate mass black holes. So the idea is this: when this is the galactic bulge, if there is so these are the galaxy moving, and if the globular cluster moves, it's animated. So as it moves, if the globular, the center, here, this actually shows a photometric brightening. But the idea is this: as the globular cluster moves, then you would see the effect of this the black hole in the center. So we observed, so we searched for intermediate black holes in the center of M22. M22 lies in front of the galactic bulge. And if you look at the proper motion of these are the M22 stars, and these are the other ones. This is the galactic bulge stars. This is, there are about 8 galactic bulge stars within 6 arc seconds of the center of the globular cluster. We chose 6 arc seconds because at 6 arc seconds, the deflection would be still deflection caused by a 100,000 solar mass black hole would be detectable even at 6 arc seconds. At 6 arc seconds, it would be more than a milliarc second. So there are about 8 bulge stars. So we looked whether some of these have been deflected within the last 20 years. So there are, in archive, there were observations starting from 1990s to 1990s to about 2024. These are in HJD now. The paper gives you all the details. So there are about 8 stars, and 6 of them are most suitable. 2 of them had only 4 epochs of observations. So as you see, this is the XY motions, and they are pretty much flat. We don't see any sign of a black hole deflection. So we find no evidence for astrometric microlensing in M22 for the observed bulge stars. So in principle, it is possible to derive mass limits, but it so happens we did a simulation with all different trajectories. We could not even put a upper mass limit because we could have missed during those between these and this, we could have missed the highest curvature. So, but this study shows that the HFT observations are in principle sensitive to astrometric microlensing signals caused by intermediate mass black holes. And this is a promising tool to make the first unambiguous detection of a black hole. How much time I have to? Okay, sorry, yeah. So now I would go to the stellar mass black hole. I will skip all this. So Yukas already showed this, but there is one more discrepancy. The black holes, the LIGO black holes are here, and the stellar mass black holes are here, and they also don't seem to be, there is very little overlap between these two as well. So we are missing somewhere. The LIGO black holes are here, the binary black holes are here. So maybe there are, if we can measure some black hole masses of single ones, it might give us some insight into what's happening here. Okay, so I don't have much time to go into this, but so I would just put this. So if you observe the astrometric event caused by a black hole, then it gives you the entire, all the parameters. So of course, the amplification coupled with the deflection tells you the Einstein ring radius, the angular Einstein ring radius. Then the parallax gives you the distance, and combining these two and the distance to the source, combining this, you get the mass. But here, you don't even use the time scale. And the time scale now, since you know the mass and the distance, the time scale now tells you the velocity of the lens again. So this is a method which tells you the mass, the distance, and the velocity from a single technique. So we have two programs, and one is to monitor long duration events. We are monitoring 5 long duration events, and in one case, we actually detected the deflection. This is not a straight line, you can see, but this is not a black hole. This tells you, it shows the parallax signal as well, and if you put all this, the mass comes out to be 0.45. Okay? So this is not a black hole, but it tells us that at least our HST observations are very sensitive to detecting black holes. If black holes, then it will be much easier. But as people pointed out, this method may or may not, it has its own bias, in the sense, if the black holes have very different velocity distribution, then this may not be the method to find. So we have another, so the correct way, or at least another way, would be to detect black holes and measure their deflection simultaneously. So we have one program to do that. We are monitoring about 1.7 million stars over 3 years. Only the brightest 10% of the stars gave us 15 events. Those are the ones we have monitored, we have analyzed so far. But there are 9 times more, 10 times more events, and analysis of that is in progress. Okay, so to summarize, so the astrometric microlensing is a powerful tool to detect black holes and measure the masses of nearby stars. We measured the mass of the near white dwarf. We found no evidence for astrometric microlensing in M22. We have 2 HST programs to detect isolated stellar mass black holes through observation of long duration events and monitoring of a large field. Thank you.
To one quick question.
If there's a really massive black hole in a globular cluster, say 100,000 solar masses, is there any prospect for that causing lensing of the stars in the clusters, either brightening or astrometric shifts?
Um, the short answer is no, extremely small. But it can cause the nearby stars, the velocity dispersions and all that. People have looked for that. And yeah, some of them do show such signatures, and that's a way to also probe such 100,000 solar mass black holes. Yeah. The astrometric microlensing is not observable.
All right, one more question.
Kailash, on the M22 constraints, are you combining all the stars together, or are you just looking individually for a shift in every one of those 8-fold stars? Can you integrate and say statistically?
Individual, because each one is at a different impact parameter. So this is a different impact parameter. So you have to now accordingly change that, the whole, the parameter space now. It changes now.
All
yeah.
right.
So we don't see anyway.
Let's thank Kailash again. And next speaker is Jessica Liu, talking about, again, well, similar finding stellar mass black holes with astrometric microlensing.
All right, so I think from this session, you're all waiting to hear if we've found our first astrometric microlensing detected black hole. I'll just get it out of the way. No. You're done. You can go to sleep. But why are we looking? Why are so many of us looking so hard? What is interesting about searching for black holes other than just sort of the novelty? I think we have a lot of really fundamental questions that we don't know about black holes still today. Isolated black holes have never been directly detected, as we've heard numerous times, although we have lots of good candidates. The major questions we're trying to address are the most simple one. What is the total number of black holes in the Milky Way? It's still uncertain to at least an order of magnitude, which is quite remarkable. What's the initial final mass relation? How do we map stars onto black holes and neutron stars? We've heard a lot about the mass gap already. That's only one aspect of that relationship. It tells us a lot about supernova physics if we can constrain that initial final mass relation. How many black holes are in binaries and when will they merge? This is critically important now for interpreting the LIGO results. We simply don't know how to make black hole binaries, not reliably at least. There's many models out there that people are debating still. And lastly, do black holes get kicked during supernovae or not? We think we have some reasonable evidence for neutron star kicks, but I think the evidence for black hole kicks is still pretty uncertain. So how are isolated stellar mass black holes, why are they so hard to find in the first place? If you just make a random patch of the sky towards the bulge, this is at around 8 degrees galactic latitude and -3 galactic longitude, vice versa. If you just take that random patch and ask how many black holes are there in this 20 arc-second field, it turns out the black holes are there. There's lots of them. Here I've just shown you this one patch from a simulation you'll hear about from my student Casey later. I didn't pre-select this to have black holes. I just took a random 20 arc-second patch. You can zoom out, you can see the black holes. They're all over the place. Similar with neutron stars and white dwarfs. Now, the hard part is that they don't lens things very often. The stellar density towards the bulge, especially at -3 degrees latitude, is actually not that dense. Especially, this comes from someone who really studies the galactic center all the time, where we are talking about incredible densities. So the lensing probabilities are small. The Einstein radii for these black holes are typically about 3 milliarcseconds. So getting another star to pass behind it at 3 milliarcseconds is still pretty challenging. But for those few events, when they do occur, we have the hope of measuring the mass, as you've heard about a lot. So what does the signal look like? In the photometry, we're quite used to seeing microlensing signals all the time that look like this. The astrometry is shown on the top here for a black hole at 4 kiloparsecs, a background source star in the bulge at 8 kiloparsecs, with a 3 arcsecond Einstein radius, as you see. What we think is probably pretty typical for a black hole event, and you can see the kind of astrometric signal we're looking for is the one in red here, right? So this is including parallax, proper motions from a reasonable distribution, et cetera. So it's a small signal that we're looking for. Now, from the photometry, we can get all kinds of information, as we've already heard, but none of it is, all of it's in units of the Einstein radius, which is not in units of milliarcseconds, but it's just a unitless quantities that we're getting out here. The astrometric signal, though, gives us the Einstein radius. I think we've heard enough about that, so I won't have to tell you very much more. What we're looking for in terms of a size of a signal is something close to a milliarc second for a 10 solar mass black hole. So that means our astrometric precision needs to be in the hundreds of microarc seconds level. And I said precision, but I really mean precision and accuracy. We have to be incredibly reliable with our astrometry over multiple years to find this signal. Okay, so we've been attempting this for quite a few years now, running on 6 years, I think. Our first round, we had a non-detection. That's the Ogle Bulge 2011 event that's up there. But at least we showed that the technique worked, because that non-detection gave us a significant mass constraint. We could prove, just as Kailash just mentioned, that we didn't have a black hole. We've been, since then, monitoring a few new targets. These are just wrapping up. They've just wrapped up this past summer, and we're in the middle of analyzing them. And one more with an incredibly long duration event, this 2014 object here, that's still ongoing, and we're still monitoring. So I will just give you a peek at why this is so challenging. So we took our last observations this summer. Why don't we have results yet? And it's because of this. Astrometry is challenging. This is a very different kind of astrometry from Gaia. We don't have the whole sky to calibrate against. We have a tiny little 10 arc second patch. And we're talking about tens of stars in the field of view to be able to define our astrometric reference frame, put everything on a common ruler. There are a lot of choices to be made, a lot of angles to be explored, including which stars do you use to align your reference frame, what's the optimal weighting, the optimal transformations, how do we optimize in the first place. All of those are things that we still have to explore for every single event, every single field. It's a little bit different. To show you what this looks like in reality, here's a data set for the 2015 event, 2015 Bulge 0029. The astrometry is color-coded by year here. What I'm showing you is the object itself on the left here, and then two other reference stars, just so you can see the astrometry. And this is starting in round one of our astrometric alignment, which is just a simple shift scale for the reference frame. And then we're going to evolve to more complicated transformation models as the movie progresses. So here's the astrometric signal that you see in this final image here. You see that this source is not linear. We see a perturbation here. Excellent news. And you can see that perturbation, though, is not there in the first round, right? So it grows with time. The key is looking at all the reference sources and looking at their astrometry and seeing how well it improves and how they all become linear as we increase the complexity of our distortion models and whatnot. And my question to you is, do you believe it? It's not a rhetorical question. You can nod or shake your head if you believe it. I see no's, I see maybes. Yeah, so this is what we're doing right now, which is, do you believe this astrometric wobble that you see right in here, given that right here and right here, these reference stars that are very nearby, within 1 arc second, look very, very straight and have reasonable chi-squareds. Okay, so this is literally where we are with the astrometric analysis. I'm pretty happy with it. I can show you all kinds of statistical plots, but I'm not going to bore you with those right now. So now let's look at the kind of event fitting that we get out of here. This is where the work is actively ongoing. Here is the photometric light curve for that same event. And this is a point source, point lens parallax model with a potential of a luminous lens in here. It can be luminous or dark as it wishes. The photometric fit is still, all of this is in progress, so it's not perfect. You see there's some long-term residuals in here. I think we're at least going to need to explore the possibility of binary lens models and binary source models. Here's the astrometry. This is as you would see it on the plane of the sky, and here are X versus time and Y versus time and their residuals. So again, you see we have a strong astrometric signal here. It looks, again, still very preliminary, but the astrometric model fit is not great at the moment, and that's mostly because the weighting between the astrometry and the photometry is still weighted by the number of data points that we have in here. So of course, the photometry is weighting the fit incredibly, incredibly high. The astrometry comes into the fit almost not at all at this point. Okay, so, and that's a choice that we have to make. And this is one that I'm very interested in other people's choices here. How are we going to weight such discrepant data? We have 10 points in the astrometry and thousands of points in the photometry. It's a non-trivial question to answer. So our to-do list here, we need to explore and make sure that we're using unbiased priors. There's a couple of simplistic priors that we're using. Again, we're fitting the photometry and the astrometry jointly, so those priors actually haven't been worked out yet in the literature. Optimal weights between these two and fitting binary models are the to-do list before we can say confidently whether there's a signal here. What is the signal? What's the mass of the object? Here's the raw parameter file that I pulled from our latest runs. And the bottom line here is the mass is quite low, about 1.3 solar masses, with pretty tiny error bars. But again, this is all very preliminary, I would say. The number of fitted parameters, as you can see, is quite large compared to a photometric fit. We have a lot of parameter space to explore. We tend to use nested sampling methods, so we think we're covering the territory pretty well. Other interesting parameters, the proper motions that we're getting between the source and the lens are all seem very reasonable given galactic models. The blending fraction, I will note, is once we've resolved it with Keck, the blending fraction indicates that we have almost no light contamination, which is really good news. But if you combine that with the fact that we get a high mass and no blending, maybe we are still detecting a compact object here, even if it isn't a black hole. The mass is suspiciously close to a neutron star mass. So that's where we are today. I just wanted to wrap up the end of the talk by talking a little bit about how we're going to get around all of these limitations of our astrometry today. We've clearly taken on a really challenging project. It's detectable. We think black holes are detectable, but they're still right at the edge, given our systematic errors. So what are we doing going forward? I'll tell you a little bit about 4 angles going forward. Current AO systems and how we can upgrade them. JWST I won't talk about much, but it's definitely on the horizon. WFIRST and TMT. So in my other hat, my other day job, the thing that generally pays the bills, microlensing doesn't pay the bills for me anymore, or yet, is upgrading the current AO system at Keck, which is our current best facility, we think, for detecting these black holes in addition to HST. So the Keck AO system, while we get great image performance, we still it's not good enough. We have to do all of our work at 2 microns. We would love to have AO corrections that allow us to go to shorter wavelengths and get higher resolution than we currently have. That improves our astrometric precision and improves our ability to do late time follow-up like Fatima talked about earlier. So we are funded to upgrade the Keck AO system quite significantly, going from this kind of image quality here as a function of sky coverage. We're usually in this domain here for these crowded fields. So current image qualities let us work at 2 microns. With the new image quality with an upgraded Keck system, which will be available in about 3 years or 4 years, we should be able to move up to H-band or possibly even J-band with diffraction-limited imaging. So that's a factor of 2 increase in spatial resolution right there. WFIRST is on the horizon, and we are very excited about WFIRST because it gives you the photometry and the astrometry for free. That's in quotes because it's not for free. There are things we have to keep our eye on it. There are things we need to do to make sure WFIRST is a killer astrometry machine. But the other thing to note is that WFIRST's other advantage is that it works in the infrared. And if we could go in the infrared, we can move into more crowded regimes where the lensing rates are higher potentially, and more black holes may reside in the disk if they don't get kicks, et cetera. So we're all very excited about WFIRST, and I work with the WFIRST astrometry team to explore the possibility of finding compact objects and weighing them with WFIRST. Okay, and then TMT, all I want to say is TMT is awesome because it's gigantic and the spatial resolution is incredible. All of the work we've been doing today is with Keck AO that looks like this, which is about a 50 or 60 milliarc second resolution. This is the kind of view of TMT of the galactic center. We're talking now 10 milliarc second resolution at J-band, a bigger field of view than the current AO system, and uniform point spread functions over the current AO systems. So incredible astrometric precisions will be possible. Something like 50 microarc seconds or better with TMT is what is in the requirement, not we hope to get there, we think we can get there. It's actually a requirement on the hardware for the facility. So that's what we're aiming for, and that will be incredible because we'll be able to measure masses of black holes, neutron stars, white dwarfs, your regular run-of-the-mill star, just about anything over a couple solar masses. We can measure a mass for you. And I think I will finish there. Thanks.
Questions? Yeah, back there.
I wonder if you thought about using information theory to decide how to weight between photometric and astrometric signal there.
Yes, there's a lot of parameters, and our uncertainties tend not to be Gaussian. So most sort of information theory approaches depend on sort of Gaussian errors, and we don't think we're in that situation. So, we can use things to, information criteria to try and make judgments, but we don't actually know the scale of what's good and what's not, what's a definitive answer.
Did you incorporate Spitzer or Gaia data into your OB 1529?
None of it is in the FITs yet. So we did the FIT independently with just the photometry and the astrometry, but it's on the list. I didn't show it, but the source that I showed has a Gaia parallax. It's really, really close. It's like 800 parsecs. So I'm not sure I believe it because it's not consistent with the photometry or the astrometry. It's in a really crowded region. We've heard a lot about Gaia parallaxes already, and the goodness of FIT out of Gaia is not great for it. So I don't know why the parallax out of Gaia might be wrong yet. Still to be explored, but I'd like to include that. All of these targets have Spitzer coverage, and that's definitely on our list to include the Spitzer photometry.
The one that you showed, you asked whether the deflection, whether you believe or not. Suppose it's real, then will you try to find out what the mass parameters would be?
Yep, that's, I think, that is the one that's shown. All the parameters that are in this plot are from that event. So the mass is about 1.3 solar masses. Yep, but with a very unblended source, where 1.3 solar masses, we should be seeing some blending there. Mm-hmm.
Is ds here the distance to the source?
ds is the distance to the source in parsecs, yeah.
And that's 3.5?
Yeah.
Kiloparsec?
That's it.
That's not a barge star, then, right?
Not a bulge star, yeah. But again, I would say this is still very preliminary, especially this is no galactic models on the priors at all. These are completely flat and unconstrained priors. So there's still a lot of space here that I think is allowed, and we can find solutions with larger distances, potentially, depending on how we change the priors.
Yeah, next question.
Yeah, so when you showed this in the talk, you said it might be a neutron star. Is there some information that can allow you to distinguish between whether or not it's a neutron star or a white dwarf?
If we can go to the blue bands, we could look in Galax. I mean, if it really is a neutron star at a kiloparsec, a white dwarf at a kiloparsec or 1.5 kiloparsecs, maybe we can see some X-ray signal in a deep X-ray observation or a UV observation.
All right, let's move on. Let's thank our speaker again. The last talk of this session is Casey Lam talking about this pop cycle, and I'll let her explain what it is.
Okay, does this work? Okay. So yeah, my name's Casey, and I guess I'm the only thing standing between you and lunch now. I'm a second-year grad student at UC Berkeley. My advisor is Jessica Liu, and this work is also done with Matt Hosek, a grad student, now postdoc at UCLA. We've been working on this code called POPSCL, which stands for Population Synthesis for Compact Object Lensing Events, and we seek to understand and model microlensing events in the Milky Way from first principles. Okay, so there's a lot of photometric surveys like OGLE and MOA. They detect hundreds of thousands of microlensing events per year, photometric. So if we want to do astrometric follow-up, though, from the ground, that requires individual candidate follow-up. So how do we select our candidates from these photometric light curves to maximize our chances for finding a black hole lens? So the Einstein crossing time is equal to the Einstein radius divided by the source lens proper motion. And since the Einstein radius is proportional to the square root of the lens mass, a heavier lens means a longer Einstein crossing time. This, though, brings up some other questions. For example, what fraction of long duration events are due to black hole lenses? Additionally, our time and resources to do astrometric follow-up are limited. So can we select on any other microlensing parameters to maximize our chances of picking a black hole lens? And also, how many black hole candidates are we actually going to need to put constraints on various black hole statistics in the Milky Way? Okay, so first, I'll explain the POPSA and POPSICLE. So we begin with a resolved stellar model of the Milky Way. We have photometry, positions, velocity for every star, then we evolve single-age components and subsets of these stars. In particular, we use the MIST models, Mesa Isochrone Stellar Tracks. And we also need an initial final mass relation for these stars. I'm going to talk about that in a moment. But then after we have this, we can turn the crank on stellar evolution, and from that get compact objects out with positions and velocities. So a little bit about the black hole neutron star initial final mass relation. It's not well understood. There's a lot of uncertainty. There's not, that we say often in introductory astronomy class, so there's some mass. Below that, you always get neutron stars. Above that, you get black holes. It's not quite true. It also depends on things such as the progenitor star's initial metallicity and the core structure of the star before the supernova explosion. So to walk through this a little bit, here you have initial mass. Here you have the remnant mass. This initial final mass relation comes from Reifel et al., 2018. And they get this from observations of neutron stars and black holes in the Milky Way, coupled with a very recent set of supernova explosion simulations. So these purple squares here are neutron stars. All these here represent black holes. You get this range depending on a parameter you choose for the supernova explosion. And so the thing to note is that for a given initial mass, you can either end up with neutron stars and black holes. So how are you going to actually implement this? You need it's probabilistic, so whether you get a neutron star or black hole at some given mass. And so to implement this initial final mass relation popsicle, we do it probabilistically. Okay, so that was all about the population synthesis. And now we're moving to event calculation. So remember, this is a resolved simulation, so we have positions and velocities for all the stars and compact objects. So that means we can propagate this forward in time. When we find two events that are close to each other in projection on the sky, we can calculate all their microlensing parameters, and then we can perform a synthetic survey that way. We can also calculate blend fraction, which is I'm going to talk about more later. So this is kind of a schematic of how that works. This would be your lens. This would be your source. All these things are neighboring stars. If you have a seeing disk of 1 arcsecond, these 3 stars here would be blended with the event. Okay, so then now we've got a list of candidate microlensing events. We can put some observational cuts and constraints on this to get out our final list of microlensing events. Okay, so now I'm going to talk about some preliminary results from Popsicle. So one thing we can do is we can figure out what the present-day mass function of black holes in the Milky Way are. So from Popsicle, and using our initial final mass relation, we get around 200 million black holes. That falls within the theoretical expectation 10 to the 8, 10 to the 9 black holes in the Milky Way. So this is the black hole mass. This is number. You'll notice there's this kind of strange gap here. That comes from the initial final mass relation we've used, in particular, those probabilistic weightings. So we also talked a little bit about LIGO in this session, and you might be saying, where are all the LIGO mass black holes? So the caveat with this and the initial final mass relation we've used is that it's for single stars of stellar metallicity. So the LIGO mass black holes are theorized to come from low metallicity stars and also may be formed dynamically through binaries. So we're going to upgrade Popsicle in the future with these things. Okay, another thing we can do is, with the simulation, look not only at photometry, but also astrometry. So here, I've run a Popsicle simulation, then impose some cuts to kind of replicate Ogle, and then plotted for the events we get out, the maximum astrometric shift and the microlensing parallax for these events. The color of the point indicates its Einstein crossing time. And then the shape of the point, squares are black holes, circles are non-black hole lenses. And so the thing you can see is that the circles and the squares, the black holes and non-black hole lenses, occupy very different spots in this astrometric shift parallax, microlens parallax space. So all the black holes are here. So the thing is, though, that this microlensing parallax can't be observed until well after peak. So we can't really use it as, say, a selection criteria when we're trying to select for black hole microlensing candidates, but we can use it as some type of confirmation by taking our candidate events and then plotting and seeing where it lands in this space. Okay, we can also use Popsicle to look towards the future and see what new W1st has in store for us. So this is from a simulation from Penny et al. 2018 using Matthew Penny's Gulls microlensing simulation. So here on the left is simulated image for W1st. Here this simulated to look like Ogle. And you'll notice that, well, two different things between Ogle and W1st. Ogle is limited to about 20-second magnitude in I band. W1st is going to be limited to about 26 magnitude in H band. So if we're staring at the galactic center, the galactic bulge, we're not going to be limited by magnitude. In W1st, we're going to be limited by crowding. And another thing that's different between Ogle and W1st, Ogle is on the ground, so it's seeing limited, while W1st, which will be in space, is going to be diffraction limited. That's interesting because of blend fraction. So the blending we're going to get is very different. So just to be clear, definition of blend fraction is the flux of the source divided by the flux of the source lens and any neighboring stars in your seeing disk. So for you might expect that if you have a black hole lens, you should have a high blend fraction because this term won't contribute. But that's only true if your seeing disk is small enough that you don't have contamination from neighbors. So if you're seeing limited, you're going to have a lot of contamination from neighbors. And so actually, blend fraction is not going to be as useful as you would like to distinguish for a black hole lens. While if you're diffraction limited, you have a smaller seeing disk, this will actually be a useful parameter. So here's two examples using an Ogle size seeing disk, and here the seeing disk is diffraction limited for W1st. And indeed, here from this popsicle simulation, you can see that black holes do have high blend fractions, while it's not true here, and this is the effect of blending from neighbors. So we can further quantify this a little bit more. So here we just consider all long duration events, Einstein crossing times greater than 120 days, and then we consider blend fractions greater than 0.1, 0.5, and 0.75. So here you can see that W1st is in orange, Ogle is in blue. W1st is going to get a lot more black hole events per area. And just want to emphasize per area because remember, W1st's survey area is going to be like about 2 square degrees. Ogle regularly surveys like over 150 square degrees of the bulge. So this is per area. But we can also look at the fraction of black hole events. So same thing here. All events have Einstein crossing times greater than 120 days, and these relative constraints on their blend fraction. And W1st will have a higher fraction of black hole events, and so that's how we can use it to select more likely black hole lens candidates. Okay, so Popsicle, hopefully I've convinced you, can tell us a lot about microlensing already, and we have some updates in the near future that we would like to add. So in particular, spatial distributions and velocity kicks that we can change this easily in Popsicle. So we're going to try to explore different spatial distributions, velocity kicks for black holes. Different initial final mass relations, in particular, one that will incorporate metallicity dependence, and also binarity and mergers, both for stars and black holes. So thank you. I'll leave my conclusions up and happy to take questions.
I would like to say, to have more details on the probabilistic function you use to distinguish between neutron stars and black holes, because I expect that the final fate of a cold-collapse supernova depends on many, many variables, such as the rotation rate, magnetic fields, metallicity, and so on. So how did you choose your probabilistic function in the end?
So it comes actually from the model itself, the Rifle et al. Paper, so I can put up the plot here. So this is this is where the probabilities come from. So they get it from their combination of observations of black holes and neutron stars and also the supernova simulations. And then they did a bunch of fits and got out these values. So you can see this here is the initial mass range. So they go between about 9 and 120. And then for all these different mass ranges, you have some probability of forming a neutron star or a black hole. And so, yeah, this basically comes from their fitting and their simulations.
It's very strange because you see that at a higher mass, you expect a black hole to be formed. Instead, you have some kind of oscillations in this probability. Is there any explanation for that?
So I think it has to do with the fact that there's a lot of different papers about supernovae, and there's different ways to look at it. So, for example, some people look at the core structure right before explosion, and that's one factor. Because we don't have beyond 120 solar masses, but for example, like pair instability supernovae, you don't even get a remnant at all. So it's very weird. It's not everything neutron star, everything black hole.
Yeah.
So it seems to me that your blending analysis can be a little bit misleading because it looks like you're taking all of the W first sources into account. But if you constrain your analysis to only the sources for which the microlensing will be well characterized, then those blending fractions should be much, much more in favor of no blending than more uniform histogram that you showed.
For W, here,
Yeah.
I'll go back.
Like this orange.
The orange one?
The orange histograms, maybe if you take into account all of the sources that W first sees, then this is right. But if you constrain yourself only to the sources that actually the microlensing of them will be well characterized, the light curves will be good enough, then probably it will change the slope.
I see.
By F blend, do you mean the fraction of flux in the source or the fraction of flux in the blend?
By F blend, I mean this.
Well, I think we can continue the discussion after.
I just want to say real quickly from Matthew's simulations, most of the microlensing events have substantial blending. So naively, what you say may seem to be true, but it turns out not to be true.
Okay.
Yeah, I think it's not quite slow. It's kind of in between the two of you.
All right, let's thank speaker again and also all the speakers from this session.